what we're doing, what this is, this class that I'm running right now, we're going to go through the refrigeration cycle in a rack, in a supermarket. We're going to cover every valve, all right, all the way through that refrigeration cycle. And while we do that, any questions that you guys have, this is tailored to you, right? I've got guys from all different levels in this room. So what I don't cover, I'm going to cover a brief overview of each valve, and then we can dig into the questions about, specifics that you have. The other thing to note is all the information on each valve or each part of the system is available information. The manufacturer can give you far more detail than I'm going to cover. Feel free to look that stuff up. What you can't get that way, and the reason we're doing this in a class, instead of me just saying, hey, read up on an A8 valve, we'll have a test Monday, right? Instead of doing that, there's no printed documentation on how this all works together, right? Once we start soldering stuff together and running pipes between them, no one is saying, well, our valve does this to your whatever, right? There's no cause and effect tied into anything. So that's what this class is really about, is understanding how each thing impacts the other thing. They all impact each other. And that's not printed material. That's not available from the manufacturers. They don't care. I'm going to make this valve, I'm going to sell it to you. You put it in, and what happens after that, it's up to you. So that's the concept. That's what we're going to be going through today. The chunk that we're going to cover today, we'll see how the time goes. We'll drag this out if you guys have a lot of questions. If you don't, we'll speed through it and move right along. But we're going to cover, really, there's 4 parts of the refrigeration cycle. There's 3 major pipes between them. We're going to cover one of those parts and some of those pipes, right? That's about as far as we're going to get. And then we'll do this again next week, right? We'll pick up and take it until we get all the way through. Does that make sense? The first question is, what is a rack? When we're all talking about a rack, you hear supermarket guys just say rack. What is that? What are we talking about? Well, here's a traditional rack. This is a pretty common setup that we'll have, and really the concept here is we're taking a bunch of semi-hermetic compressors and we're putting them on a metal rack. That's where the term comes from. Doesn't necessarily look like that anymore. Some new stuff definitely doesn't, but that's where the term came from. It's just a metal shelf that our compressors actually sit on, and that's why we call it a rack. Here's a couple more versions. The rack in the box. We haven't seen a lot of those in the last few months that I've been with Kalos, but they are out there. These are protocol racks. This is a complete refrigeration rack system. We call it a rack in the box because it's just a cabinet that houses everything. Very, very snug, very tight. We have to be able to access the back to get to the oil separators and stuff like that, but it's got it all. It's all crammed in there. These guys are actually pretty cool. You can drop one of these in a place that wasn't a grocery store, and you don't need a giant grocery store. We typically see these in small groceries that are in a strip mall, that type thing, where somebody takes over a Beals and they cut half of it into a grocery store, and then they'll drop 4 or 5 of these inside the store, different places. Then this guy next to him on the right, there are the 2 shelves with the green compressors, CO2 transcritical, right? So you can see the rack. It's pretty obvious. That's as modern as it gets. This is where we're going today, right? Everything is shifting to that. This is the cutting edge. Same idea, same concept, right? So going all the way back to that first one I showed you from the 80s, 1980s, when that rack was built, 83, 84, something like that, to today, right? Very similar setups. So the other thing that's really common when we talk about a rack system, once we line out all of our compressors, we're going to tie them all together. We're going to do that through common, what we call headers, right? The header is a pipe that we run that ties their suctions together. So all the compressors share one suction. All the compressors share one discharge, all right? So that's what that, this picture is demonstrating. I've got compressors, and I can see I've got these little pipes coming down from one common pipe. We call that pipe our header, and we're gonna have one for suction and discharge. So that changes the dynamics of my compressor. Once I take it from being on an individual circuit, and I pipe it together this way, I'm gonna get an average suction now. Instead of, as my box gets colder and colder, my suction pressure falls. That's what we're used to seeing on a single circuit. That's not gonna happen anymore, right? Because now I'm averaging everything out. So as my box gets colder and colder, my load lightens, and instead of my suction just falling, I'm gonna turn off a compressor and maintain, right? So things start changing once we pipe them together this way. The other thing that we're gonna do is, we're gonna do the same thing for our load, all right? Normally we would, on an individual circuit, I got one suction pipe that goes to one evaporator. That's kind of the standard setup. When I go to a parallel rack system, I'm gonna bring in all of my suctions, tie them into one common pipe, and that's gonna tie into that suction header for my compressors. I'll probably have 2 suction headers, one for my load, one for my compressors, and they will be tied together. All right, they'll be the same pipe. 2 physically different pipes, but one big one in between them, making them the same. Right? So that's what that's an example of. And for you guys that aren't really familiar with supermarkets, each one of those pipes, each one of those blue lines represents a circuit. There's probably 6 cases on each one, up to 6, on each one of those lines. So, just doing some quick math there, you can see 40, 50 evaporators, something like that, is not uncommon. We can get up to 80, 82 to 85 is a large store rack system. They can go all the way down to 12. We've seen some pretty small stuff too. So it all depends on what the store needs. Okay. So when we're talking about a rack, that's what we're talking about. So everything we're discussing today is that general setup. Now there are lots of variations on that. We're going to talk about the quote typical. What do you, when you walk into a store and it's a supermarket, what do you expect to find? Now there's going to be variations, and here's, this is the exciting part about this business. It's very uncommon that you find 2 systems exactly the same. There's going to be something different. Each one's can be customized. Each one has had different things done to it over the years. Each one of them's trying something new. Each one of them's got, we just decided to sell lobsters here, right? But we're not down the street, so it's got a different setup, right? Those kind of things happen. So there's a lot of generalities that are the same, but there's a lot of each store is unique, right? So when we're talking about that, you can see I've got the legend up here. Let's talk about how do I know, right? I walk into a store, I got all this stuff that's different. How do I know what is different? What do I need to know? The engineering is going to tell me that. If I look at the engineering, it's going to help me understand what this rack is actually doing. All right. So before we start and we go through the whole system and everything else, I want to go through how we read the engineering and what is available to us and what we should be looking for. Okay. So this picture that you're seeing up here, can't really tell any detail on that. This is right out of our blueprints. All right. That's where this is. So my startup text. Hopefully you're very familiar with those. They're actually on different pages of my blueprints. One is giving me all the engineering for my circuits, and then underneath that, I've got all of my engineering for my compressors. That's great as long as I have my blueprints, right? My service techs are walking in the 1984 store, probably not so much. This is what you're going to find instead. This is the bread and butter of a service tech. We call this the legend. Right? I know you all thought I was the legend, but really that's the legend. Alright, yeah, they don't get any better, by the way. Alright, so the legend is taking that engineering that we just looked at right out of the blueprints, and it's putting it in one place, and it's putting it on one sheet, okay? This should be mounted physically to the rack, and there's lots of different versions of this based on the rack manufacturer. and the engineer who's did the blueprints, okay? But every rack came with this piece of information at some point. Now, whether it's been updated for the new cases that were installed or not, that's up to the contractor who did that work. The engineer provided it, all right? But sometimes they don't get stuck to the door. If not, at least I know how it started, right? So let's go through it. Let's talk about what are we gonna get out of this thing. In that case information, in that first top left-hand chunk, one of the biggest, most useful things that I'm gonna pull out of that, model number for the case, which sounds ridiculous, but we do reskins quite a bit. When a case gets very beat up, we replace the sheet metal and the tag either disappears or may be wrong. You know, I mean, somebody had to print them out and stick them on the case that wasn't the case manufacturer. So it's very often that that's just not right. Case model number right there. Here's another one. How many times have you guys been working on a TXV in a walk-in box and wondered, is that the right TXV? Model number.
Ryan has.
Model number's right there. It's on the legend, right? You don't have to guess. You can look it up. It's right there. The distributor. Should I have number 1 or number 2? Right? It's on the legend. You don't have to guess. The BTUs. All right, so let's first off, on a legend, all of my BTUs are going to be written in MBTU. So I just want to make sure you guys all know that is times 1,000. That's BTUs to get BTUs out of MBTUs. We start looking at some of these loads. I think a lot of you will be surprised who haven't been looking. How big these loads are, or how small actually. You know, some of these are quite small. When we think they're gigantic, it turns out that they're 2 tons or 2.5 tons, right? But that's because of our suction. It's because our suction pressure runs much lower in refrigeration.
Teacher, question. This is just what you were talking about earlier. Like, not a big deal. I was trying to clear, get my knowledge. You said a parallel rack.
Correct.
So my understanding back in the day was parallel rack. You have 4 or 5 compressors, but they're all the same size.
So you're thinking parallel because they're all the same size. So the term parallel rack, and it's actually duplex parallel rack refrigeration is what I'm actually discussing. The term parallel comes because they're piped in parallel, not series, all right? So for instance, a compound cooling compressor that pulls in low, discharges interstage, sucks that back in, and then discharges out, that's series. Okay, so a compound rack that does that, you got 2 or 3 compressors that are low temp, they discharge to a mid-stage, then they use that mid-stage as suction for 3 more compressors and pump it up the rest of the way. It's not a parallel rack, all right? That's a series, that rack is in series. When I have my racks with my compressors all using a common suction header and a common discharge, they are piped in parallel. And there's your parallel rack.
So our compound coolers on low temps are still parallel racks?
So they are, because we're using the same suction header and they're doing it internally. Right, does that make sense? That CO2 rack that I showed you a picture of just a minute ago,
System.
the compressors on top are low temp, the compressors underneath that are medium. The discharge for those low temp compressors is into the suction for the medium. So it's 2 parallel racks that now I've piped in series. Right, so that's not a pure parallel system. All right. Not to get too complex, but there you go. So as far as he was talking about, y'all are my compressors being the same size, we'll get into that. We're going to cover staging. That's going to be one of the things in this class, and how that works and why. Okay. If I slide out to the right on my legend on this, we're still looking at my cases. One of the next most important thing that we're going to find, my SST. All right. So when we're talking about our saturated suction temp, we're talking about the temperature the pressure, PT chart, right? That is going to give this to me in temperature. I need to know this. What is that pressure? Okay. What is the temperature I want the refrigerant to boil in my evaporator? Okay. That is one of the massive differences between air conditioning and refrigeration. I am controlling everything. Everything is about getting that pressure correct. Right? If I get that pressure right, I can predict the temperature that box is going to run, that case is going to run, right? Because of the PT chart. So I'm controlling everything to pressure, based on the saturated suction temperature. Well, that means while I'm working on something, I might want to know what its SST is, right? What is my target? What am I supposed to be doing? Of course, everything's about that. So it's on my legend. There is my SST. I can look up case information, I can try to pull it off the internet, I can try to find out what this weird W in the model number means and why none of that engineering is right anymore, right? You guys, you've all been there. Yes, we have customers that require the manufacturer to build equipment special for them. They buy, oh, I love your Cadillac, but you know what, it needs wings. So, put wings on it, and then we're gonna put a model number, we're gonna put our letter in your model number so everybody knows that one ain't the same as all the rest, right? Well, we find that constantly. So when you look online and you try to get that case information, it's wrong. Legend's right. Okay, it's gonna have your SST. How many amps should my defrost heaters be pulling? How many times you guys asked that question? Right? I got heater out, or do I not? Okay? Legend's gonna give you that. It's gonna show you. Okay? How about liquid line solenoids? We ran through a string of incorrect solenoids, right? Guess what? They're on the Legend. Right? You don't have to guess which size it is. Which EPR is supposed to be there for that circuit. It's on the Legend. And then the last one is an interesting piece. We don't need it every day, but how long is our pipe run, right? There are times when that is useful. When I'm getting ready to set an EPR and I'm trying to figure out how much pressure drop I'm gonna have from my rack, where my EPR is, to my case, I might wanna know, is that 87 feet or is that 215, right? That might make a difference. I'm gonna have a significant drop with that longer run, okay? And I need to know that. So I'm probably gonna pull it up there. Another reason I might use that is, I'm gonna pump this thing down, how much refrigerant am I gonna be moving? Right? Look at this thing, it's 1 3/8 pipe and it's 300 feet. Yeah, it's probably not gonna fit in my 25. And the end pipe size, that'd be the next piece. So,
Teacher? So as far as like the pipe length and pressure drop goes, is there like a general rule of thumb, like, all right, for every like 150 feet, that's like
Yeah.
5 pounds?
yeah, that's a good, the general rule of thumb, right? It's always gonna be different than this general rule of thumb, but this can give you an idea of what to expect, right? You should be able to expect about a 2-pound drop, roughly 2 PSI, for about a 100-foot run, right, on the suction side. And that's ballpark, you know, it'll always be different than that, but that will get you something pretty close. It's all gonna depend on how many 90s, right? That's one of the reasons why you're seeing a lot of racks on the roof, and then the early stores, they were all in a mezzanine or downstairs, you know, they're all low. That's because we had to go up, over, down, right? There's a bunch of 90s right there, just making that happen. If I'm on the roof and I just drop down and drop right into my case, I got less drop.
And each 90 is like a couple feet, I think.
Short radius is 6 foot.
Well, we don't use short radius ever. We should.
Long radius should be 3 foot.
Yeah, so 3 feet every 90 roughly. Around there.
3 feet,
Yeah.
a 90s, right, is what it's worth.
Yeah.
If your pipe is sized properly, so that's the next question. It's gonna tell me what I'm supposed to have, right? If I'm sitting there and I got a 14-pound drop, and when we're talking about drop, we're talking about suction pressure at my rack versus at my evaporator. 14 pounds different, something like that, that's crazy, that's a huge drop. So now I'm looking at why, right? Well, one of my first questions, there's only one reason why I've got that much drop, right? I've got more refrigerant flowing through that pipe than that pipe can move, that's why, all right? So I've got one of two things wrong. I've got too much refrigerant in the pipe, TXV flooding, for instance, right? Or the pipe's the wrong size, right? They have a rubber ball in it that's making it half size, it might have a plug, right? Or we installed the wrong size, right? You know, I've seen this, unfortunately, 1 3" coming over to the top, drop to 7/8, and then go back to 1 3". Looks at 1 3 on both ends, everything looks great, there's this 7/8 stick in the cylinder. What? I don't know why, right? That's why I got a 14-pound drop. That's why my cases are on warm, right? When I force on all my compressors, that one case makes temp,
Yeah.
right?
Might even have that scrap.
And of course, that's how you're gonna find it, right? You're gonna find when you find these problems, you're gonna find someone has made it work, right? They had to. That, you know, why am I running a 6 PSI suction on this rack? It's calling for 12. Okay, and when I take it to 12, I got this one lineup that just falls out. Oh, why is that? All right, this will tell me. I can look at this and it'll give me the size, not only of my suction horizontals, but it will give me my risers. We assume all of our risers are one size down. That's not always the case, right? It's all based on enough velocity to push that oil out of those traps. Sometimes that turns out to be a different number than one size down. This will give that.
Can you explain what a riser is?
A riser is something that goes up. Okay.
Like caffeine.
All right, so suction riser, for those that didn't hear, he asked, what is a riser, right? So a riser is when I'm running my refrigerant piping, and we're particularly talking about suction, all right? The suction side of my case to my compressor is gonna be a significant distance, and I'm gonna have to change elevation, all right? If I'm going down into the floor, and I'm going through a pit, then I'm coming up to go to my compressor. That would be my riser, right? If I'm going up to the ceiling and then across the entire store and then down to my compressor, my riser is going to be the part going up from the case to the ceiling, all right? My challenge is, you guys know about, you know, any system that's just a compressor and an evaporator. I'm passing my oil out of that compressor. It's flowing through the entire refrigeration cycle and coming back to my compressor. That's why my compressor doesn't run out of oil, right? Well, when I'm designing that, because that my oil is gonna travel through the whole system, I have to be careful about my piping, okay? When I'm trying to get that oil to come out of my evaporator and return back to my compressor and go through that piping, I've got to size that piping properly so that I get enough velocity. All right, so when we're talking about a riser, and we're talking about that up and down piece, that's where I have problems. I've got to lift oil up, and I've got to carry it all the way out of the pipe. And if it doesn't make it all the way out, if it goes up halfway, 3/4 of the way, it doesn't make it all the way out, it's gonna fall, right? What's under there? My evaporator, right? So that oil's gonna log in my evaporator. That's what's gonna happen. So I've got to help it. I got to help it go up. The way I'm going to do that is to pick my velocity up to get my refrigerant flowing faster, right? So if we think of a big river and it's got a little narrow and then it gets wide again, what's going on in that narrow, right? That's where you want a kayak, right? It's going to be exciting. Whitewater, we got rapids, right? Because the water's running way faster because I've got the same volume just going through a smaller space, so it's going really quick. All right, so we're going to do the exact same thing. We're going to take our refrigerant, our suction line, and we're going to shrink it so that the amount of refrigerant flowing through there is the same, but it's going to go way faster, right? That'll help that oil jump up and get all the way to the top. Now, what's the downside? That's pressure drop. It's inefficiency. I got to run compressors to pull down to a lower suction than I really need because I've got this drop, right? So when we ask, how many feet is a drop? 2 PSI for 100 feet. How big's my riser? That's gonna change that, right? If my riser's really small, may only be a pound, right? If it's really big, could be 3, okay? So that matters. So it's a loss of efficiency. What we need to understand is a riser, reducing my riser to get my oil back costs me horsepower every day, every minute that my compressors are running, all right? It costs me horsepower. That's wasted energy. Right? But it is required because I've got to pull that oil back. So it's balanced. I don't want to go too small. I don't want to go too big. Right? I want that engineering to be right, and that's why I'm getting it off my ledge. Subcooler data. Here's another one. All right? This is another one. When I walk into a store, I gotta know what is my liquid temp supposed to be. All of my cases are engineered based on that liquid temperature. Right? If there is no subcooler, right, then it's going to be based on ambient, ASHRAE ambient, 95 degrees probably here in Florida, right? It's going to be based on worst case scenario, right? 95 degrees. if there's no subcooler data at all. That means there is no subcooler and 95 is good to go, all right? But the majority of the stores we work in actually have mechanical subcoolers. If they have a mechanical subcooler, then I'm taking credit for all of the heat that I'm removing from that liquid when I'm sizing my liquid lines, when I'm sizing my TXVs. Taking credit for it, all right? That means I need to know what that temperature is, and I need to verify I have it. Okay, before I touch a TXV, before I even think about superheat, I'm gonna confirm that I'm feeding that valve with the proper liquid, right? I mean, we know that. We will never adjust a TXV until we're sure we have a solid column of liquid. We will never adjust a TXV until we know that the liquid is at the correct temperature. We'll never adjust a TXV if we don't know that we have enough pressure, right, on the liquid line. The liquid must meet those three conditions before we can even begin to use the superheat data we're getting, before it's even meaningful.
Yeah, typically we'll find when we get the subcooler working, because they're never working when we go.
It's a giant problem, right?
You end up getting a massive flood back on a lot of circuits, and then if you go to the circuits in Tech Assist, and you see the work orders generated, there's usually typically like a lot of work orders for that, and that's because the subcooler wasn't working, nobody checked it, and you go to the expansion valves, every single one of them all the way open. Or you'll see every single one of them has a new expansion valve, and that's all the way open too, because they say, oh, well, it's not working, I'm not feeding it.
Yep, the new one didn't work either.
Yeah, so change the TXV, open it all the way up, still got 20 superheat, gotta change it again.
So why does that happen? What he just described, unfortunately, is not uncommon. It's actually very common. You know, why is that? It's mostly because people don't understand how critical a subcooler is, right? And that's why we're covering it, and we're gonna cover it in depth in this course. We're gonna go through the subcooler. That's why I'm showing you the engineering data. It's one of the first things you should be checking when you go to the store. When you walk in a store you haven't been in before, right? Before you walk in that store, meet the store manager, shake hands, start pulling product, grabbing my gauges, screwing it on, checking my superheat, pulling out my rent. Oh, wait. Yeah, I missed a couple steps there. All right, we can check superheat, but once again, we don't even know if it matters until we confirm those three things, right? Well, in order to confirm it is at the right temperature, I have to know what is the right temperature. There is no standard, it's always X. It's not. Right? I think it's common. Right? If you came to me and you said I had a low temp rack that was running a subcooler at minus 40, I'd probably say, are you sure? Because that's not common. Right? Seems maybe that's wrong. Right? For low temp, we like to see somewhere between 40 and 50 degrees. That's typically what we see. Have I seen 20? Yeah, absolutely. I've seen it several times. Okay? That's cold. That's enough to freeze, right? Have I seen 60? Yep. I don't know why, right? You know, I don't know why. Doesn't matter. It wasn't my call. It's what the customer asked for. It's what the engineers developed. So because they developed it, everything is sized on it, we need to know what it is, right? Medium temp typically runs a lot warmer, right? I've seen a bunch of 50-degree medium temp, but I've probably seen a lot more 70-degree. So my point is, you kind of learn what's normal, but you gotta look. You gotta look. Each one's gonna be a little different, right? And I gotta know where to get that. I'm gonna get that off of my ledger. So another interesting piece is BTUs. Out there on the right, 65.9 is my MBTUs on this guy. That's interesting. So what does that tell me? That's telling me how many tons of cooling I'm removing from that liquid line. That's what that's telling me. Well, every ton, every BTU that I pull out of that liquid line is equal to a BTU a compressor has to do. They're 1 to 1. All right? Well, the other interesting thing about this is it's telling me it's being subcooled from B rack, from a different rack. Okay? So that means I've got 65.9 MBTUs of work that's being done by a different rack. Let that sink in for a minute. All right, that means if my subcooler's not working, it's turned off, that's 65.9 MBTU of compressor I need on this rack, I don't have. Oh, I don't have enough capacity, right? That's a problem. So if I want to know how much capacity I'm short, my MBTUs are right there. That's about the only thing we're going to use it for, is figuring out what's going to happen when I turn this guy on, horsepower-wise. Or if I have to shut this off, how big of a hole am I going to be in, right? I can look at it and figure that out right there. The next one, off to the end there, 47. What's my SST on a subcooler? It's got an EPR, it's got a TXV, right? That means I can set it up just like a case. That means I need to know what its target SST is, right? This was 47. So this is a low temp rack, this particular legend that I pulled. It's a low temp rack. 47 PSI, 47 degrees on my PT chart, that's above medium temp, right? Well, you guys know, we lose efficiency as we drop suction tremendously, right? So low temp rack, if I'm taking 65, 66 MBTU of compressor off of that, if I put that on that rack running at 7 PSI, you guys know that's going to be about a 20 horse compressor, right? But if I'm doing it at medium temp, that's about a 5 horse compressor, right? That's why my efficiency is so dramatic. That's why I have to use my subcooler. Okay, that's on my legend. All right, my compressor data. This is one of those mysteries, right? We walk into a rack and I got a compressor staging wildly, and this one's bigger than the guy after. Doesn't make sense. Looks like somebody put the wrong compressor in. Happens. We get technicians who lose a compressor. They go to get a compressor. They need one. It's an emergency. The rack's not maintaining. They call. We don't have a 228, but I got 337. Yeah, what's your pipe? What's the size of the pipe? Yeah, it'll work. Send it. Right? Happens. Sure it happens. How do we know? Right? How do we know that's what's going on? How do we know that's our problem or not? Well, guess what? All the model numbers that are supposed to be on that rack are on my legend. So I can look. Is that what I have? Right? If it's not, and the program doesn't know that, it's staging incorrectly. Okay? My flows may be wrong. Maybe why I've got an oil problem. Maybe why the whole rack's shutting off and then starting back up. Right? Depending how grossly missized it is. But that's going to give you that data right there. It's MBTUs. Once again, this is fascinating. We think of these giant compressors being, 20-ton compressors, 30-ton compressors. Question is, at what suction pressure? The lower that pressure gets, those BTUs start shrinking for that same horsepower, right? That's right here. We can look at it and see, this is a 5-ton compressor. This is not a 20, right? Some of us did that at class recently, right? We went through that. The suction temp those compressors are designed to run at. So they're all going to match the suction for the rack. This is the first place you can find it. You'll find it in a few places on this legend. But I need to know, what is this rack supposed to be running? Right? I walk up, I'm sitting there at 25 PSI, my target's 25, everything in the store is running 8 degrees warm. Right? I might come over here to my legend and see, what is it supposed to be? Oh, somebody fat fingered that. It's supposed to be 15. Right? Somebody hit a 2 instead of a 1. Right? How do I know that? My legend right here is going to tell me. This rack is a minus 13 degree rack. It's going to give me the horsepower for those compressors. It's going to give me all of my electrical data. RLA, FLA. You guys know your lock rotor amps is 6 times your run. I don't know if you guys knew this. Often on your compressor data sheet, it'll give you one or the other. Does it give you both? You can figure them out by dividing and multiplying. My legend will have them both, though, just so you know. That's true for everything, not just compressors. That's fan motors, everything else. Cooling. So, and we're going to talk about cooling and compressors here in a minute. But you walk into a rack and there was a head fan, you can see that somebody has removed the head fan, right? Is it supposed to have a head fan? I don't know. My legend will tell me that. Why would that have happened? Well, either the fan went bad and tech pulled it and didn't replace it, or I've had a refrigerant conversion and my heater compression's changed and that compressor no longer requires that, right?
Or it's got some other means of cooling.
Or it's got another, or it needs more, right? Head fan wasn't enough, and now I've gone to liquid injection, right? I've gone to a Y10 valve, right? Something like that. And we'll talk about all that, what those are, and why we would use them, why we would select them. But as a technician standing there, all I know is that it used to have something it doesn't have, and I don't know why. My legend is gonna answer that question for me. It will tell me. Can you see my little dot? Not really. It'll say head fan, it'll say
Yeah, it's a,
de-superheating valve. Okay, that's the terminology they're gonna use for injecting liquid or vapor to cool it down, right? It'll say whether, it'll just tell me, either one of them there. How about unloaders? Unloaders bolt on and off, okay? So one of the things to remember when I order a compressor, if I order the exact replacement and it had an unloader, the model number will tell that part supplier I need an unloader, right? Well, here's the challenge. Most of our replacement compressors are made without unloaders. So I call up United and I say, I need this model number, and how many times have you heard this? There's 2 in the whole country, one's out in California, it'll be here in a week. What? All right, if you've got an unloader, that's why. They're gonna ship you a compressor with an unloader, because that's what you just ordered, that's what you asked for, okay? But your unloader bolts off the old compressor. You can get a regular compressor and move the unloader yourself. You give him that model number, he's like, yeah, I got 3 in the shop right here, you want them in an hour? All right? So just know that, right? If you've got an unloader, it's gonna slow down your order significantly, right? You may wanna get that. If you got time, it's no big deal, whatever. But if it's something we wanna get going, right? Have them get you the model number without the unloader and move the unloader. All right. The other reason I need to know, did this compressor come with an unloader, is because of that. That means technicians pull out a compressor with an unloader on it and don't move it, and they just put in the regular compressor. Happens all the time, right? Time crunch, whatever. Make 50 excuses, but that's what happens. So I walk in, once again, I got staging problems, okay, and we'll talk about why that's a problem as we get going, as we go through this. But that's one of the things I'm gonna need to know is when you'll hear me say, did you validate your horsepower, right? What I mean is when we're looking at these swinging suction problems in a heavily cycling rack, I mean, do you have the right compressor? Is it the right size? Does the computer agree with the size that's sitting on the rack? Is that compressor delivering that horsepower, right? Do you have bad valve plates, right? Do you have compression problems, okay? If it thinks it's a 20 horse compressor and that compressor's only giving you 15 because one of the pistons ain't moving, we need to know that, right? Okay? And does it have an unloader? Is it unloading? If you put your amp meter on this compressor and you force the unloader on and off, does it change? Right? Does it change? Because computer's expecting it to. If it doesn't, that's why we got problems, right? So when I say validate your horsepower, that's what I'm talking about. Well, that means I need to know, my legend says I'm supposed to have an unloader, I see that's a replacement compressor, there's no unloader on that. There we go, right? Now, the fix, do I put an unloader there, or do I change my staging? That's gonna be up to our customer at that point, right? Unless we did it. If we did it, we're going back with what the legend says. We have to match our engineering. But if the customer made that decision because that's the compressor they could get, and their guy didn't know how to move the unloader, didn't know about that, hadn't been through this class, right? Could be an additional cost. We'll just ask them, what do you want to do? Do you want us to put this back? Or you just want to type with your fingers and change your staging, right? It's up to you. The other bits on here, my condenser information. All right, for us down here, and we will get into low ambient controls. All right, we will talk about that, probably won't get into that today. But 50% splits, 25% splits, are they active? All right, were they installed originally? Okay, that's all gonna be in here. Model number, you guys know those condensers, 20-year-old condensers, you can't read a thing on that plate. It's just white, you can barely even tell that was the plate. Well, the model number's right here, okay, it's on my legend. The TD, right? So when I'm trying to calculate, is my condenser working? Does it work? I need to know what is my TD. I'm gonna measure that. And I'm gonna know what TD is producing. Is that right? 4? Does that sound good? Yeah, that sounds great. Right? Maybe it's 12. I don't know. Right? My legend is gonna give it to me. I don't have to guess. Okay? That's a summer problem, right? That's not our winter problem. That's, that 325 head. I'm trying to figure out why, right? That's where I'm at.
You're talking about temperature TD? Like thermometer?
Yeah, my refrigerant coming in versus coming out.
Oh, okay, so you're saturated.
Right.
Not your TD.
And then your other, there are two, there's a delta
Delta
TD,
and-
is my air blowing through versus my refrigerant coming out.
Yeah.
All right, so when we're trying to understand have we lost capacity, our fins rotted out of this thing, if we're not exchanging heat, it's full of oil, something's going on. We're gonna know that by measuring the delta, right?
Yeah.
The air blowing through my coil versus the temperature of the refrigerant coming out again. How many degrees is that? Right, how does that change? Okay. And then the valve information, all right? So there's tons of valves on this thing. I'm gonna have solenoid valves that are normally open instead of normally closed, and we'll talk about that. That means I better get the right valve. I mean, just think about what I just said. Hot gas going into a condenser through a normally open solenoid. That solenoid fails, I walk into a store, hey, I need 1 1/8 inch. Yeah. Normally closed, that's what they're gonna give you. Every time, right? So I gotta have the model number. I gotta have the model number on that. It's on here. The check valves for my 50% splits, on here. The solenoid valve for the bleed off line. It's on here. I don't have to guess, right? We just went through this whole thing with solenoids recently. Their size matters,
Yes.
right? Their capacity matters. If I'm grossly oversized, it won't close, right? If I'm undersized, it's a restriction. The hole inside is smaller than the pipe. Okay? If that happens and I get the wrong one, it's just not gonna work. When we're talking about pump out solenoids on a condenser, I don't have any idea how many BTUs that thing's moving, right? Guess what? I don't have to. Somebody else does, and they did that math and typed their answer right here on this sheet. Okay? Suction data, the rack SST. This is where the official, this is a minus 13 degree rack. Right, when we start talking about racks, what's your rack? I got a minus 25 rack, I got a minus 23 rack. We're not talking about supply air on my coldest case. We're talking about what is that SST target that rack runs at. Remember, our suction pipe is a common pipe between all of my compressors. That's the pressure I expect to find in that manifold is my design SST. Right? In this case, it's minus 13 degrees. So the other thing I've got to know is my refrigerant type, right? I take my refrigerant type and I plug that in to my PT chart, and that will tell me the pressure that I should find on that manifold.
Is that calculated off of midpoint?
PT Pro's the way to go.
All right, so yeah, and we weren't going to get into this, but you brought it up, so here we go. The question he just asked, is that based on midpoint? All right, so let's talk about glide for a moment, because this is definitely one of those things that guys stumble on, all right? Talking about glide, good old R22 has no glide. So when I'm taking superheat, I'm taking subcooling, I'm setting EPRs, I'm setting up my suction on my rack, it's the same number. My PT chart's gonna give me one number, I just use it, right? Guess what, CO2 is that way too. One of the nice benefits of going back to CO2 is more glide, right? The problem is when I start blending a bunch of refrigerants together that are different refrigerants, yeah, that's what all of our mixes are, right? There are three or four different refrigerants, and I'm just blending a percentage of them, shoving them in a bottle and giving them a new name. You're 449. No, you're not. You're R32, R123Z, right? Right? These are three, and that one's got an HFC in it. Don't remember which one. I'm taking four refrigerants and I'm cramming them into the same container. Well, that means, like it or not, I got four PT charts. They're not the same. So they've got a different boiling point, they've got different condensing, right? So when I blend them all together, the one that boils first, right, that's gonna be my bubble point. Okay? The one that condenses, right, they're gonna be different. So I'm gonna end up with a range of pressure temperature instead of just a fixed pressure temperature. It's gonna be a whole range, right? That's what we call glide. That's what we're talking about, right? So what we've got to do when we set superheat, we're boiling our refrigerant. We're going from a liquid to a vapor, right? We want to measure that based on when that first refrigerant just starts to boil. Well, that means the later refrigerants haven't even begun to boil, right? Okay? That's going to be our dew point. When that refrigerant begins to boil, we want to measure that on our PT chart. We're going to do that math based on dew point. And this is stupid, but it works. Super duper, right? Dew point, superheat, super duper will keep you straight, all right? Now, like I said, it's stupid, but it works, right? Now, the other side of that is condensing, right? So I'm going to start condensing. The exact same thing is going to happen. It's going to be a different refrigerant, but the one that condenses first is the one I want to measure first. That's my bubble point, all right? So when I'm figuring sub-bub, it's even stupider than
No, it does not seem stupider.
subcooling, bubble point, subcooling, bubble point. All right, those two go together. That's the other end of my glide. Now, that leaves me with one more value that we need. If I pick up a drum of refrigerant out of my truck and I strap a thermometer to it and I hook my gauge up to it, is that going to give me dew point or bubble point? Neither one. What the hell is going on? Alright? Neither one. When I am at saturation, I do not have bubble or dew. I am literally halfway in between. Okay? Right in the center. At saturation. Right? When I say saturation, I'm talking about I have liquid and vapor present at the same time in the same place. Okay? If I have liquid and vapor and I add heat, I'm going to boil refrigerant. Right? If I have liquid and vapor and I remove heat, reject heat, right? I'm going to condense some of that vapor into liquid. That's what's going to happen. That's going to give me a nice, stable, predictable pressure-temperature relationship that we think of as the PT chart. But now I got a problem because it's halfway between my dew point and my bubble point, and it's not on my chart. Is it predictable? Yeah, it's absolutely, completely predictable. Right? And we need to know it. It's just not one of those two columns, right? It's what we call midpoint. Right? When you hear midpoint, we're talking about blends of refrigerant that are at saturation. Okay? Why does this matter? This matters a lot. First, how do we calculate it? Simple. We take our dew point, we take our bubble point, we add them together, divide by 2. It's the average. right, halfway between. That's gonna give us our midpoint. We don't have that on any of these fancy apps, right? They're not showing us midpoint. Why do we need to know midpoint? Well, in air conditioning, we don't. Doesn't matter. In single refrigeration circuits with a compressor and an evaporator, we don't. Doesn't matter, right? I just told you for setting superheat, we're gonna use dew point. When we're figuring subcooling, we're gonna, so why are we using midpoint? SST in my evaporator. Oh, that thing that I said everything is based on? Remember that? That's saturated suction temp. Saturation, midpoint. Midpoint, right? This is a big one. Guys, don't understand this. It is not taught well, and it is definitely not passed around from tech to tech very well. This is one of those things that just saturates our industry that's just wrong, all right? And it is SST, that saturated suction temperature, the temperature I want the refrigerant in my evaporator to actually boil at is midpoint. All right? So that means when I'm setting my EPR, my evaporator pressure regulator, to control that pressure very precisely, I'm setting midpoint. Right? When I'm setting up my rack to run at minus 13 degrees, that's 13 degrees midpoint. Okay? Not dew point, not bubble, mid.
I know
Yes,
like the, I mean, this is,
He raised his hand.
there's a, I know like on the E2s, there was, like after we did like gas conversions, we had to reprogram, like change the SST, but in the program you had, bubble or dew, like there wasn't like mid.
Yeah, there isn't. Correct. So if you're controlling a TXV, you can choose dew because you're calculating superheat. If you're running your subcooler or you're staging fans trying to get free cooling or whatever you're doing there, it's subcooling. So you use bubble. The only time that you must have midpoint is at saturation. So that's going to be setting up the rack and setting your EPRs. It's the only way that it could be. Now, electronic valves, typically when they're controlling EPRs, and you put in pressure, right? They're looking at PSI, not temp. If you put in temperature, they're looking at the case temp, the supplier. So they're not doing the math for an EPR, which they are for the TXVs, right? So that's why you're not seeing midpoint in the programming. It's typically not required. Right? They're not actually controlling to SST, they're controlling to PSI. Somebody's already done the math. And as we saw in Jacksonville, maybe incorrectly, right? We just started up a new store, the 449 refrigerant, and the legend is typed in dew point.
Yeah, seen that
Yeah.
several times.
And everything ran really well. Really cold.
Really fun.
Really fun.
Right? All circuits were cycling, every circuit in the store cycling. The rack's 10 PSI too low, right? They're shoveling coal into the power plant behind the building, and everything is really chilly. It did not need to be. Right? The engineer dismissed that.
Could be 3207.
So, and that's what I'm saying about this is just one of those things that it saturates our industry incorrectly, right? We had an engineer who's trained to do this, messed up, right? Forgot dew point, or midpoint. Okay, so a couple other tidbits of information that are useful here. My suction sock, all right? When I say sock, suction sock, that's a slang term that technicians use. I'm talking about the suction filter, okay? On my rack, my suction filter is replaceable. Well, if I'm doing a PM or I'm doing a project and I need to install one before I start the project, what am I buying, right? There's a bunch of different sizes, a bunch of different kinds. I can't walk in and say, hey, I need a suction sock, right? I gotta crank out a model number, RL5, right? Well, where am I gonna find that? On my legend, okay? And the accumulator model, because we change accumulators every day. Just kidding, we hardly ever change accumulators on a rack. But if something happened and I needed to, it is also on my legend. Then there's this whole note section where this is, the engineer is telling you, the only reason they typed all these notes is for you. You are the end user who's going to read this. When I say you, I mean the service technician standing in the rack. That's who these notes are for, right? There's all kinds of data they can give us here, and I listed these specifically because they were on this particular legend, but there's a ton of stuff that's useful. Total BTUs. Interesting to know, it's one of those things we just don't talk about. I got a 40-ton rack, right? I got a 120-ton rack. Do I? I don't know. Never looked. Well, now you know you can. My refrigerant type, all right, this is the big one. This is probably the most important thing on the whole damn sheet. All right, we change refrigerant types so many times in these stores with these conversions. We're doing it all the time. How many times you walked into a store and you just didn't know? Right? You look, there's a tag that says R22 on that thing. There's something that says 404 in the corner, but there's an empty 447 bottle, so, and then I got mystery gas over here. I don't know what the heck is in this rack, right? Right? How am I calculating superheat if I don't know which PT chart to use?
PT current.
Right? No way. Okay? If I've got to add refrigerant, come on, baby.
Sender.
Or we could look at the engineering, right? And that's what you hear everybody say. Look at the engineering. What's your engineering say? I don't know. Where do I look? On my legend, and it's going to be in this bottom right-hand corner of my legend where my general information is, where those notes are, right? The oil separator, pipe size, heat reclaim data, receiver information, compressor safety, the compressor safety model numbers. Here, I wanted to point that one out for a minute, right? So you guys have been through my compound class, and you've heard me talking about the difference between oil safety for a Carlisle and a Copeland. They're different pressure. So, but that leaves us in an awkward position of standing in front of the counter at United saying, I need an oil safety, and he's pulling it out, and me going, that's a 9 PSI, I need a 6.5. He's like, what? Right? Well, I can give him the model number, it's on the legend. Let's talk about the refrigeration cycle for a minute. The first piece that I want to cover, when we talk about our systems, we're talking about DX. We've all heard that term, DX. What we mean is direct expansion, all right? That's what DX stands for. When we say that, we're talking about this refrigerant cycle, all right? There's other ways to do refrigeration. There's other ways we can do this, absorption, flooded evaporators, all that kind of stuff, right? When we're talking about taking a refrigerant and putting it through our metering device and it changing states, that's the expansion, okay? Direct expansion, that's what we mean. So when we say DX, we're talking about this, right? When we talk about other things, right, we're not talking about this, okay? Now, the reason why I'm clarifying that is because our parallel rack systems we're going to talk about in here today, in this month, are going to be all DX. That's what we're going to be discussing, right? We do have a few alternatives out there, like I just said, and we'll talk about those too. But as long as we're talking about DX, then there's a couple things that we need to be sure we understand what we mean when we say, all right? The first one is saturation. You guys just heard me talk about that for a minute. I can't overemphasize how critical it is that you truly understand. When I say saturation, what I mean is liquid and vapor together in the same place at the same time. That is saturation. Okay. At that saturation, this special condition exists where our PT chart can predict pressure and temperature. Right? If I am not at saturation, my PT chart cannot predict my pressure-temperature relationship. I must have liquid and vapor at the same time, same place for the PT chart to work. Does that make sense? All right. If I take that refrigerant and I boil it all off, and I've got nothing but vapor left, and I keep absorbing heat, all right, that is what superheat is. All right, so when we say superheat, We mean we have boiled all of our refrigerant into a vapor, and we're continuing to add temp heat. Right? We measure that by figuring out what its temperature would be for the pressure that it's at, if it was at saturation, and then we're calculating the difference, and that'll tell us how much superheat, right? That's how that works, all right? Just like that, going the other way, if I condense that, if I'm at saturation and I continue to remove heat, all of that vapor will eventually condense to a liquid until it's 100% liquid, right? If I keep cooling that, I'm gonna fall off my PT chart, right? And I'm gonna be subcooled. That's what subcooling is, right? I'm just cooling it beyond saturation, right? Same thing, I can't predict that, how much heat I take out of that, what's my pressure gonna be, my PT chart won't work anymore. But I can use my PT chart to calculate how much of that subcooling I have, right? I just wanted to clarify that because we're gonna use these principles through every part of our system. So if we don't understand that, when we walk into a refrigeration rack house or a supermarket, we cannot look in the pipes. We don't have the ability. So we're gonna use our pressure gauge and our temperature probe. That's the only way we can look at the pipe. That means we need to understand these three things implicitly and know what should be happening at each place in this system, and then we can measure, is it, right? Is that what's happening, okay? So we've got to understand these principles. They're basic, simple principles that we were taught back in air conditioning school 101, right? Back in the early days, okay? They still apply today. They apply, this refrigeration cycle is our refrigeration cycle, right? This applies to the ice maker in the dorm room that's cranking out half a pound a day, right? Or that 182 case rack. They work exactly the same way, right? So just as a review, I'm going to run through this very quickly. This is not a refrigeration 101 course, right? But I am going to point out the key components of this, what's happening there, and then we're going to go through a rack and do the same thing. All right? So let's start with compression. Compressor is the heart of the system, so to speak, right? It's creating a suction on one side, a low pressure on one side, and it's creating the high pressure on the other. My refrigerant in the entire system, there's no pump moving that refrigerant. Right? The way that refrigerant is moving is it through the entire loop. Everything beyond that, it is flowing from high pressure to a lower pressure. Right? High pressure will always flow to low pressure. My compressor is simply creating the highest pressure there is the outlet of that compressor. The lowest pressure there is the inlet to that compressor. So the refrigerant that is discharging is going to find its way to that lowest pressure. That's how my refrigerant moves. Right? That's what causes it to move. My compressor is not pumping that refrigerant, it's creating a high and a low pressure. Okay, we call it the pump, sure. Pumps move liquid. That refrigerant coming out of that compressor, what state is it in?
Superheated vapor.
Superheated vapor, right? I have superheat on that discharge gas, right? I have superheat. How do I know that? If I take my PT chart and I take that pressure, it's not going to be on my PT chart. That temperature is going to be higher than my PT chart, right? Every degree that it's higher is 1 degree superheat. So I've got superheated discharge vapor, and it's going to flow to my condenser, and my condenser, I'm going to reject heat, right? How am I going to do that? Well, in our world, we're just going to take ambient outside air and blow it through the coil, right? That's going to absorb some of that superheat. How much of that superheat? All of it. All of it, however much there is. Right? I've got to get that refrigerant to saturation. It must be at saturation. That's how my condenser is going to condense, is by rejecting all of my superheat. So if I've got 280 degree hot gas coming out of this compressor, and I look at that refrigerant type, and my ambient is 95 degrees, and I plug that in there, and it says I gotta reject 80 degrees of superheat, that's how much superheat's gotta come out. Right? That's one of the reasons why we gotta control how much superheat's in that discharge. If I have too much, the condenser may not be big enough. Right? That can happen.
These superheaters, that's what you need.
Yep.
All right? Okay, so then I come out of my condenser. Now I've rejected all of my heat. I've gotten to saturation, and I'm gonna probably reject a little bit more, right? I'm gonna subcool that liquid just a little bit. Okay? Now I've got my subcooled liquid coming out of there, and it's gonna flow to my expansion device, right? I'm at high pressure, subcooled liquid here, all right? My expansion device is really just a restriction. It's a giant restriction. It's a little tiny hole in a big pipe, and I've got a compressor sucking on one side and pushing on the other. So that's gonna create my low pressure zone, right? My subcooled liquid is gonna go hit that little hole and change from a liquid to a vapor as it changes pressure instantly, right? It's gonna flash. Sir?
It's not a liquid or a vapor, it's saturated.
All right, so what's actually happening inside of my evaporator, all right, he's making a point. I'm not boiling it all off yet. It's actually coming out of that expansion device, and this is air conditioning more than refrigeration, where you sometimes get that pipe that's showing on that drawing, that expansion line, they call it, right? In our world, that would just be the distributor.
Right.
Right? That's all we got. We don't have any piping there, but we may have a distributor, right? In that distributor, what I'm gonna have is atomized refrigerant. Little tiny balls of liquid. That's what I actually have, right? With some vapor. And that's gonna flow into my evaporator, and I'm gonna flood. The majority of my evaporator is gonna be liquid.
Yep.
Overwhelming majority of it.
Where's the module?
Right? Depending on the efficiency of my evaporator, that's gonna determine my superheat, what percentage of that is I'm actually changing state in. All right? So the last, ballpark you can hear, around 10% or so, or less, of that evaporator is vapor. All right? So the first part is 100% liquid, the last part is 100% vapor. Everything in the middle is gonna have refrigerant boiling out of it. Right? So it's gonna be different percentages. As we work towards the top, obviously a higher percentage of vapor. Okay? Go work towards the bottom, liquid. Right? So that's how that works until I absorb all the heat that I can. I have now changed state of that refrigerant 100% to vapor. I've left my SST. Okay? Once that's happened and I continue to add heat, I am adding superheat. Right? I was at saturation and I boiled off, so I'm 100% vapor, and I keep adding degrees, superheat.
Is it true that 400 blend refrigerants, the manufacturers want more of a flooded coil? So like typically around like 3 to 5 sometimes you gotta get to.
Yep.
To achieve what they want compared to like if you're doing R22, where you might go get away with like 8 to 10.
So, and honestly, I don't believe it's got, and I may be wrong about this, but I don't believe it's got as much to do with the refrigerant as it does with law on efficiency. All right, so let's back up for a second. All right, superheat, every degree of superheat that I add, my compressor is going to have to discharge into the condenser, and then the condenser's got to reject it. Right? Every degree of superheat I put in, I have to spend energy to take out. That doesn't sound efficient at all. That would mean, how much superheat do I want?
As low as possible.
0, right?
That's 100% efficient for
Right.
your case.
If I want to be 100% efficient, I must be at 0% superheat, right?
I was just gonna add, so basically, the only reason we even have superheat is to protect the compressor.
Yeah,
That's it.
yeah, no liquid coming back.
That's it.
Which one across small?
Ideally, in a perfect world, we would have zero superheat
Correct.
all the way across the board.
Yep.
But compressors don't fall.
Well, when we start talking about flooded coils, that's why, because they have 0 degrees of superheat. That's why we use them.
That's why you can't have negative superheat.
That is so cool.
So anyway, we're coming out of our evaporator with now cold refrigerant vapor that is technically superheated. Okay, based on the temperature of that evaporator, that will tell us how cold. All right, and then we're gonna feed that into our compressor. Now we've completed our loop, right? Everyone has seen this 1,000 times. This particular one, probably even more than normal, because it's from HVAC school, if you notice. Had a few choices there. Does that look a little more, yeah, a little more similar, right? So here's the same drawing. This is the same drawing. For you guys that are not familiar with supermarkets, we can see we have 3 evaporators there. They're just showing us 3 different ways to control that. That's the part that normally we would have 80 something, right, or 40 in there. All right, so here are my parts. I got compression on the left. Right, the red line is my superheated discharge. It's going up to my condenser. That's the second circle up there, right? I'm coming out of my condenser as a subcooled liquid. That's the blue flowing down. It's flowing to my TXV. Right? I don't have that expansion line between my TXV and my evaporator. I just have a distributor. So I've only got those 3 parts, and then it's going to flow right into my evaporator, and I come out with the green line right to my compressors. Boom, there's my loop. All right, it does exist. It is supermarkets. All right? We've got a couple other things going on. We've got a few valves in these pipes. And that's what we're going to talk about. We're going to go through these chunks. What are these chunks? And how do they apply to us?
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.